Hi everyone, I thought I'd better do a video demonstrating the roots of polynomials formulae that we get, why they actually work, because, I'm just throwing these facts at you without proving them, and that would be an awful thing for me to do as a maths teacher. I'm a big fan of proof anyway. It's the only way we can be certain that I'm not lying to you, and you should always doubt what I say. So I'm sure you've learned that, if nothing else, in my class. Okay, so let's take the quadratic case first, because it's easy to show with a quadratic case and with the cubic case. Yeah. So I'm going to try and prove to you that if the roots of a quadratic are alpha and beta, then alpha plus beta is minus b over a, and alpha beta is c over a. So a general quadratic is ax squared plus bx plus c equals 0. And let that quadratic have roots alpha and beta. Now, with any quadratic, and in fact with any polynomial, and this is going to be a trick every single time we do one of these proofs, you could divide by a first, giving you x squared plus b over ax plus c over a, and that would equal 0. Okay, so what you might think? Well, let's look at this fact over here for a second and just say, if it's got the roots alpha and beta, then x minus alpha, so just using this second fact, if you like, yeah, then x minus alpha multiplied by x minus beta would equal 0. Now, the reason I'm saying that is because if the roots are genuinely the solutions to the equation, then you could always rewrite the equation like that. Because remember, we could have, like I say, initially divided through by a, and then we don't have to have a coefficient before x here or here. And you can do that with absolutely any quadratic. You might be sort of almost wary there, thinking, well, surely some quadratics you need a 2 or a 3 or a 7 or whatever before one of those x's or both those x's. It's just not true. If I can take an example, yeah, if we take a quadratic which can be factorized, something like 2x squared plus 3x plus 1. Can that be factorized? let me come up with a quadratic that can be factorized. I'll tell you what, I'll start with the quadratic form first. And I'm kind of going off on a little bit of a tangent here. Let's say you had something like this, yeah? I just want to show you that you can always write this with just an x in the first place. Obviously, that's 6x squared minus 3x plus 4x. Well, that's plus x and then minus 2, yeah? Well, what we could have done with both of those equations is divided them both by 6, yeah? What happens to this one if I divide it by 6? I get x squared plus x over 6 minus a third, okay? So far, so good. What happens to this one if I divide it by 6? Well, I could divide this bit by 2, giving me x minus a half, and this bit by 3, giving me x plus 2/3. You still have exactly the same roots. It doesn't change the value of the roots. And 0 divided by 6 in both cases is still 0. So, and by the way, that factorizes to give that. If you wanted, if you multiplied that out, I bet you get exactly this now. Yeah, let me just show you. Multiply it out, you get x squared minus a half x plus 2/3 x minus 2/3 times a half. Well, that's going to be minus 2/6, which is minus a third equals 0. I believe if you combine those two, you will get a positive 1/6, because that's minus 3/6 plus 4/6. You do get positive 1/6. So do you see what I mean? You can always write any quadratic with just a leading coefficient of 1. And that is the trick, really, in this roots of polynomial proof. So I've gone on a slight little tangent there just to demonstrate that you can definitely always write it like this. Well, there was a really good reason for that, because now the proof is going to be easy, because all I need to do is multiply out these brackets. I get x squared minus alpha x minus beta x plus alpha beta equals 0. And that gives me x squared minus x times alpha plus beta plus alpha beta equals 0. Now, this is supposed to be exactly the same quadratic as this one. Yeah, it's supposed to have exactly the same properties. Well, now I can just look at it and say, thus, by equating coefficients, and I'll just put equating coefficients, we have b over a. Well, that term must be equal to the x coefficient here, so that must be equal to minus alpha plus beta, and c over a, and that's this term, must be equal to alpha beta. And that easily gives us the result minus b over a is alpha plus beta, and c over a is alpha beta. Yeah, that's how it works with quadratics. And the good news is, does it work any different with cubics, quartics, quintics, heptics, septics, and all the other ones? Yes, it works exactly the same. So the cubic case. Okay, let ax cubed plus bx squared plus cx plus d equals 0 have roots alpha, beta, gamma. Yeah, if it's got those three roots, then we could write it in two different ways. We could write the cubic unfactorized or multiplied out like this. This is essentially the argument. You can write the cubic in two different ways. You could write it like that, having divided by whatever the coefficient of x cubed is, the whole expression. 0 divided by a is still 0. But if it's got the roots alpha, beta, gamma, then I could also write it in factorized form as x minus alpha times by x minus beta times by x minus gamma equals 0. And once again, all I'm going to do is multiply out the brackets. Now, I've already done this first one. I might as well use the result up here and say that's the same as x squared minus alpha plus beta times x plus alpha beta. So I'm just multiplying out the first two brackets there. And then I'm going to multiply all of that by x and then multiply all of it by negative gamma. So let's multiply it out carefully. X cubed minus alpha plus beta x squared plus x alpha beta plus, minus gamma x squared plus gamma x alpha plus beta minus alpha beta gamma equals 0. Okay, so I only just squeezed that in there. So let me give myself a bit more space. I've basically just got tidying up to do now. So let's give myself a bit more space. We get, I don't know why I'm using that first bracket. Well, because it's all, yeah, that first bracket is unnecessary. Where's my rubber? I don't really need that. Okay, so I've multiplied it all out now, and you'll notice 1, 2, 3, 4, 5, 6 terms because I've done 2 times 3 there. Always count your terms and make sure you haven't missed one. It's easy to do. So what do we get at the end of it? We have an x cubed. Now, let's combine now this x squared and this x squared. If you think about it, I've got minus alpha x squared minus beta x squared and minus gamma x squared. Well, I could collect all those together to say minus x squared alpha plus beta plus gamma. Lovely. Tick when you've done it. And now for the x terms, let's underline those in blue. Here we go. I can put all of those together and say, well, if I've got alpha beta x, I've got alpha gamma x, and I've got beta gamma x, I can put all those together as plus x times alpha beta plus beta gamma plus alpha gamma. Forgetting what gamma looks like there. And lastly, so I've done that term, and lastly I've got minus alpha beta gamma. By all means, I fully invite you to multiply it out yourself there. And now, at the end, we just equate coefficients again. So we've got b over a. That should be the same as minus alpha plus beta plus gamma. I've got c over a. That should be the same as alpha beta plus beta gamma plus alpha gamma. And then I've got d over a. Well, that should be the same as minus alpha beta gamma. And that easily gives us the result. Minus b over a is, if I can use the quick way of writing it, the sum of alpha. C over a is the sum of alpha beta. And d over a, minus d over a, sorry, is alpha beta gamma. Hope that made sense. That's just a quick example of the proofs. I fully invite you to do it for the quartic case. It takes a bit longer, but I wouldn't be being, a good teacher, I think, if I didn't leave the most difficult, hardest work for you, the student. Okay, I hope you enjoyed that. It's just a quick video. Well done, and hopefully keep watching. Hopefully this one gets more than 0 views, which I have noticed some of my videos are getting. Okay, bye-bye.